If you try to launch, I don't know, 100,000 traditional threads on your machine right now, your system will just instantly choke. Like, it'll run out of memory and crash. But if you launch 100,000 Kotlin coroutines, it barely breaks a sweat. How exactly does a language completely bypass the operating system's heavy limitations to pull off that kind of concurrency?
Well, it's an incredible trick of the compiler, really. I mean, you aren't actually bypassing the operating system. You're just completely reimagining how work is scheduled within the constraints of the Java virtual machine.
Right.
It's just a fundamental shift in managing execution.
Welcome to our deep dive into Kotlin coroutines, asynchronous flow, and Android app architecture. For you, the listener, whether you are prepping for a senior technical interview or, maybe just trying to untangle a massive legacy code base, the goal today is to shortcut your way to mastering modern asynchronous programming.
Yeah, and we're working from a really fantastic stack of sources today.
We really are. We have the official Kotlin documentation, the Android developer architecture guides, and a highly detailed translated cheat sheet of notes that honestly looks like it was smuggled out of a senior developer interview prep session.
Okay, let's unpack this. Because dealing with background tasks has historically been a nightmare of callback hell and memory leaks. So before we can dive into complex streams of data, we need to establish the foundation.
Right.
We need to look at that claim about the 100,000 coroutines. What is the actual mechanical difference between a coroutine and a traditional thread?
The difference really comes down to who is managing the work and, the associated memory overhead. A traditional thread is managed directly by the operating system.
Okay.
So when you create one, the OS allocates this massive block of memory for the threads stack. If you, say, rent a thread to go fetch some data over a network, and that fetch takes 2 seconds.
That thread is just stuck.
Exactly. It's completely blocked. It just sits idle, holding on to all that memory, unable to do anything else. Coroutines, on the other hand, are not managed by the OS. Oh, interesting.
Yeah, they're lightweight user space abstractions managed entirely by the Kotlin runtime. Over 50% of professional developers using coroutines actually report increased productivity because of this.
Our sources use a really good analogy here. They compare traditional threads to renting a massive, expensive bulldozer for every single task on a construction site.
I like that.
Right? It's overkill. And if the bulldozer runs out of gas, it blocks the whole road. Coroutines are framed as a highly coordinated team of nimble workers who can, pause their tasks and hand off tools without blocking the site. But what actually makes them nimble? Like, how do they just step out of the way?
The workers are nimble because of a mechanism called continuation passing style, and that's triggered by the suspend keyword.
Right, the suspend modifier.
Yeah. When you mark a Kotlin function with suspend, you aren't just adding a label. You are telling the Kotlin compiler to aggressively rewrite that function into a state machine under the hood. So when your coroutine hits a network request and needs to wait, it doesn't block the underlying thread.
So what does it do?
Instead, the compiler takes all your local variables, like everything you were working on, and saves them into a small continuation object.
So it literally just packs up its current workspace into a box.
Precisely. It packs up the box, stores it in memory, and then completely releases the underlying thread back to the application.
Wow.
Yeah, so that thread is now totally free to render UI, handle button clicks, or run entirely different coroutines.
And then what happens when the network comes back?
When the response finally comes back, the Kotlin runtime grabs an available thread, unpacks the continuation object, and resumes the exact line of code where it left off. That's why you can have 100,000 of them.
Because you aren't creating 100,000 OS threads.
Right. You're just creating small, highly efficient state machine objects.
I mean, I have to push back a bit on the practical reality of this, though.
Okay, go ahead.
If a coroutine is suspended and the runtime is just juggling all these state machines, we still need physical threads to do the actual heavy lifting, right? Like parsing a massive JSON file or writing to a local database. Doesn't that still pose a risk of locking up the app if it ends up on the wrong thread?
What's fascinating here is how Kotlin solves that exact routing problem using dispatchers. You're absolutely right. I mean, the work still requires a physical thread.
Right.
Coroutines use dispatchers to determine exactly which thread pool executes the work. To protect your app from freezing, you utilize a function called withContext.
Okay, with context.
Yeah, so by wrapping your heavy database right in withContextDispatchers.io, you are explicitly telling the coroutine to pause, shift its execution over to a background thread pool specifically optimized for I/O operations, do the heavy lifting there, and then shift back.
Which means the main UI thread remains completely unblocked and totally oblivious to the heavy lifting.
Exactly. It's called mean safety.
That makes sense. But if I'm looking at your own code base right now, listener, or if you're staring at memory leaks in your crash logs, this interview cheat sheet has a massive red flag you need to check. It explicitly says never use global scope.
Oh yeah, never.
But if these state machines are so lightweight, why is a global scope such a severe danger?
Because of the principle of structured concurrency. If you launch a coroutine in global scope, its lifetime is bound to the entire application process.
So it just lives forever.
Basically, let's say a user opens a profile screen in your app, and you launch a global coroutine to download a high-resolution image. Before it finishes, the user gets bored and hits the back button, destroying that screen.
Right, the screen is gone, but the global coroutine has no idea.
Exactly. It keeps running in the background. It continues consuming bandwidth, processing the image, and then trying to deliver to a UI that literally no longer exists in memory. That is a textbook memory leak, and it drains the user's battery for absolutely no reason. Structured concurrency forces you to tie your coroutines to a specific lifecycle. In an Android context, you typically bind them to a view model scope.
Okay, so tying it to the view model.
Right. When the user leaves the screen, the view model is cleared, the scope is canceled, and every single coroutine running inside that scope is aggressively and cleanly canceled.
So the workers are forcibly told, hey, the site is closed, drop your tools.
Exactly.
That handles a single asynchronous task perfectly. But what happens when the requirements scale up? Say we aren't just fetching a profile picture once. Say we need a continuous stream of data.
Like a live feed.
Yeah, livestock prices, a real-time GPS location feed, or a chat database that updates every time someone types a message. A single suspend function returning one result isn't enough anymore. We need to move from puddles to rivers. We need asynchronous flow.
A flow is Kotlin's implementation of reactive streams. It handles a continuous emission of data computed asynchronously. Structurally, it's divided into three distinct parts. You have the producer, which generates and emits the data. Then intermediate operators, which modify or filter that data as it travels. And finally, a consumer, which actually collects the final values.
The official documentation leans really heavily on the fact that these flows are cold. For someone visualizing this architecture, what does cold actually mean at runtime?
Cold means that the code you write inside the flow builder is completely inert.
Inert, like it doesn't do anything.
Right. You can write the most resource-intensive, complex stream imaginable, fetching from a server, parsing millions of rows, and it will consume 0 CPU cycles. It doesn't run until a terminal operator is invoked. Usually that is the collect function.
Oh, I see. So a suspending function is like asking for a glass of water. You wait, you get it once. But a flow is like installing plumbing. The pipes are laid out, the intermediaries are connected, but the water, the data, doesn't actually start moving until someone explicitly walks up and turns on the faucet by calling collect.
That captures the lazy nature of it perfectly. And those intermediary pipes are highly versatile. You have standard operators like map to transform an emitted integer into a formatted string, or filter to drop invalid data, or the transform operator to do both. But the mechanics of where these pipes run introduce a major architectural trap.
Oh, right. Because if I'm inside a flow builder and I hit a heavy database query, I'd naturally just wrap it in with contextdispatchers.io to push it to a background thread, exactly like we just discussed with coroutines. It solves the problem, right?
You would think so. But Kotlin will actually throw a runtime illegal state exception and crash your app if you try that.
Wait, really? Why?
Because it violates a core rule called context preservation. A flow is strictly designed to execute in the context of the coroutine that calls collect.
Ah, I see.
Yeah, so if your main thread starts collecting, the producer runs on the main thread. If you try to force a context change inside the flow builder itself using with context, the compiler panics because the downstream collector loses control of where its data is coming from.
So how do you get the heavy database work off the main thread if the language actively prevents you from using with context inside the stream?
You must use the flow-on intermediate operator.
Flown.
Yeah. You attach flow-on-dispatchers.io to your stream. What this does mechanically is quite brilliant. It creates an entirely separate coroutine for all the operations upstream from it, running on the I/O thread pool.
Oh, wow.
And then it sets up a hidden channel, a communication buffer, to safely pass the emitted data down to the collector running in its original context.
Okay, but that implies the producer and the consumer are now running concurrently in two different coroutines, which introduces an inevitable timing problem. What if the producer is incredibly fast, like a stock ticker emitting 50 updates a second. But the consumer is slow, perhaps struggling to render complex UI graphs.
This is back pressure, and Flow gives you explicit tools to handle it. If you use the buffer operator, you decouple the emission rate from the collection rate. The producer rapidly fills up a memory buffer, and the consumer pulls from it as fast as it can.
But what if the consumer truly cannot keep up?
Then you use conflate, or collect latest.
Which just drops data.
Exactly. If the producer emits values faster than the collector can process them, conflate deliberately drops the intermediate unprocessed values.
Okay.
The collector will finish its current task and immediately grab the absolute most recent value, ignoring the backlog. It ensures the UI is always displaying the latest state.
Rather than slowly animating through outdated historical data, that makes sense. Let's escalate the complexity. In the real world, apps rarely rely on a single, isolated stream of data. You have multiple streams interacting. How do we stitch them together?
The two most frequent composition operators are zip and combine, and their underlying mechanics dictate very different use cases. Zip strictly pairs corresponding values.
So it waits.
Yes, it will halt and wait until both upstream flows have emitted a new, uncoupled value. It's useful when you need to match exactly one request with exactly one response. Combine, however, is eager.
Eager in what sense?
Whenever either of the upstream flows emits a new value, Combine immediately recomputes its result, pulling the most recently cached value from the other flow.
Oh, I get it. Like a checkout screen. You have a flow of the cart total and a flow of the currently selected shipping method.
Exactly.
If the user changes the shipping method, you don't wait for the cart total to change. You immediately combine the new shipping cost with the existing cached cart total to render the final price.
Got on.
That makes perfect sense for parallel streams. But what about a flow of flows? Let's say I have a search bar. The user is typing letters. Every time the text changes, a flow emits the current string. And for every emitted string, I need to trigger a network request that returns a new flow of search results.
That requires flattening. And the choice of operator here dramatically impacts performance.
Okay.
If you want the request processed strictly in order, you use flatmap concat. If you want all network requests fired concurrently, you use flatmap merge.
Yeah.
But for a search bar, neither of those is optimal.
Why not? I mean, if I type Kotlin, that's 6 keystrokes, 6 emissions.
Because if you use flatmap merge, you fire 6 concurrent network requests. They might return out of order. The response for KOT might arrive after the response for Kotlin, completely overriding the correct UI with outdated results. This is where flatmap is magic.
How does flatmap solve it?
Mechanically, when a new value is emitted from the upstream, like when the user types the next letter, flatmap actively cancels the flow generated by the previous value.
So it kills the old request.
Yes. It throws a cancellation exception to the in-flight network request for KOT the millisecond the user types the L. It actively saves the user's battery and bandwidth by killing obsolete work at the network level.
Here's where it gets really interesting, though. What happens when that network request completely fails? Because networks fail constantly. The documentation explicitly states you should not wrap your flow builder code in a standard try-catch block. If I can't use try-catch, how do we handle a server timeout without the app violently crashing?
This is the principle of exception transparency. A flow stream should never secretly swallow exceptions inside its producer. Doing so breaks the predictability for the downstream collector. Instead, you use the declarative .catch intermediate operator.
Okay, let me challenge that logic. If I'm catching an exception using the .catch operator, doesn't that just swallow the error anyway? The stream still stops collecting. From the user's perspective, the screen just goes dead. What if I still want the app to show a network failed retry button?
That's precisely why the .catch operator is so powerful. It gives you control over the failure. Inside the catch block, you aren't just logging an error, you have the ability to emit an entirely new value into the downstream pipe.
Wait, really?
Yeah, so when the network throws an I/O exception, your catch block intercepts it and emits a specific error UI state object. From the collector's perspective on the UI thread, the flow completed gracefully, but it received an actionable piece of data that tells it to render the retry button.
So the error is transmuted into just another piece of valid data flowing down the pipe. That's incredibly elegant. We've built these resilient cold pipelines. But this brings us to the harsh reality of Android architecture.
The UI.
Yes. UIs are not patient consumers. When a user rotates their phone, the entire UI activity is destroyed and recreated from scratch. It does not want to wait for a cold flow to boot up, reconnect to a database, and emit a value. It needs data instantly.
Which is exactly why we have to bridge the gap between cold data streams and the demanding nature of user interfaces. We need hot flows.
Hot flows?
A hot flow is always active in memory. It holds state and processes events regardless of whether anyone is currently collecting it. You can convert any cold flow to a hot flow using operators like shareIn or stateIn.
This is exactly what the senior developer cheat sheet highlights as an absolute must-know interview secret. The critical difference between StateFlow and SharedFlow. For anyone listening who needs to make architectural decisions tomorrow, break down the mechanics of these two.
Okay, so StateFlow is specifically engineered to hold the current UI state. It requires you to pass in an initial value upon creation, meaning it always has a state to expose. Most importantly, it conflates updates.
Conflates, meaning if my network request returns the exact same list of users twice in a row.
StateFlow intercepts the second emission, realizes the data hasn't changed via an equality check, and simply drops it. It prevents your UI from performing an expensive, redundant re-render. When a recreated screen subscribes to a StateFlow, it instantly receives the cached current state.
That sounds suspiciously like live data for those migrating from older code bases.
They serve identical purposes, but with a critical lifecycle difference. Live data is deeply tied to Android. It knows when the UI goes into the background and automatically stops observing data. StateFlow is a pure Kotlin construct.
It doesn't know what Android is.
Right. It has no idea what an Android lifecycle is. If you launch a standard coroutine to collect a StateFlow in the UI, it will keep collecting, rendering, and consuming resources even when the app is minimized. You absolutely must use the Android-specific Repeat on Lifecycle API to explicitly tell the collection coroutine to suspend when the user backgrounds the app.
Okay, that's crucial. And SharedFlow, where does that fit in?
SharedFlow is the generalization of StateFlow. It's designed for broadcasting events, not holding state. It does not require an initial value, and by default, it does not conflate identical values.
Yeah.
Every event is pushed downstream. Furthermore, it gives you deep configuration over its internal buffer.
The cheat sheet notes mention replay caches and on-buffer overflow policies. How do those actually work?
The replay cache allows you to specify exactly how many past events should be immediately blasted to a new subscriber the moment they start collecting. But the on-buffer overflow policy is the real architectural tool. If your SharedFlow emits events faster than they can be consumed, you decide the behavior. Suspend halts the emitter. Drop latest rejects incoming events until the buffer clears. But drop oldest is fascinating.
What does that one do?
It evicts the oldest unprocessed event from memory to make room for the new one, ensuring the stream keeps moving at the cost of historical data.
You know, a good mnemonic for the listener here, think of StateFlow as the thermostat on your wall. It requires an initial temperature, it conflates changes, like if the temperature stays at 72 degrees, it doesn't keep notifying you. And anyone walking into the room instantly sees the current state.
I love that.
But SharedFlow is a doorbell. It's an event. There is no initial ring. If you aren't standing there listening when it happens, you miss the event entirely, unless, you configure a weird doorbell with a replay cache.
If we connect this to the bigger picture, you use StateFlow to drive the persistent pixels on the screen. The text, the lists, the toggles. You use SharedFlow for transient one-off events, showing a toast notification, navigating to a different screen, or triggering an animation.
So we've built these incredibly powerful, hot event streams, but if we just throw them everywhere in the code, like if a junior developer injects them directly into a UI button click, we'll end up with a tangled mess.
Yeah.
We've essentially recreated the chaos of callback hell in a new format. Where do they actually belong?
This is where we strictly enforce unidirectional data flow, or UDF. The Android architecture guidelines emphasize a rigid separation between business logic, which is what the app actually does with data, and UI logic, which is how the app displays it.
Yeah.
To enforce this, we use stateholders.
Like the view model.
Exactly. The view model is the primary business logic stateholder. It sits between your raw data repositories and your UI. It takes the cold data flows, applies business rules, and exposes them exclusively as hot state flows. Because the view model survives configuration changes, when the user rotates the screen, the UI is destroyed, but the view model lives on in memory, holding on to that state flow so the new screen can instantly resync. And for simpler UI-only logic, like deciding whether to show a bottom bar based on screen size, you just use a plain class stateholder tied directly to the UI lifecycle.
But let me ask a pointed architectural question here. If the view model has all this perfectly formatted data and business logic, why shouldn't I just pass the whole view model instance down into every single UI component? Let the header, the submit button, and the list all grab what they need directly from the instance. Sounds like a time saver.
Oh, absolutely do not do that. Passing the whole view model destroys the reusability of your UI.
Why?
If you build a sleek, generic submit button component, but you force it to accept a profile view model as an argument, that button can now only ever be used on the profile screen. Furthermore, it completely destroys the principle of single source of truth. If 5 different UI elements all have a direct reference to the view model, and they can all independently call functions to mutate the state concurrently, you introduce massive race conditions. Tracking down a bug becomes impossible because you don't know which component triggered the state change.
Ah, I see.
In UDF, state only ever flows down from the view model as an immutable stream. User events, like a button click, flow up as simple intents. You should only ever pass a UI component the exact primitive piece of state it needs to render.
Keep it strictly need to know.
Exactly.
The state is the truth, and the UI is just a dumb reflection of that truth. Well, what a journey this has been. We started by escaping the crushing weight of OS threads, diving into the compiler magic and continuations of lightweight coroutines.
Yeah.
We built robust, cold plumbing systems with asynchronous flow, mastering context preservation and active cancellation. We bridged the gap to the demanding UI using the hot caches of StateFlow and SharedFlow. And finally, we organized it all cleanly behind the unidirectional data flow pattern. So what does this all mean?
Well, we've seen how reactive streams gracefully handle unpredictable asynchronous events in an app. It represents a fundamental paradigm shift in how you think about control. Instead of rigidly forcing step A, then step B, you set up smart systems that simply react to the world as it happens.
Right.
This raises an important question for you, the listener. Where else in your daily life or your workflow are you micromanaging the steps when you should really just be setting up a stream to react to the flow?
A brilliant thought to end on. Remember, you don't have to build the entire house with one massive bulldozer. Thank you for joining us on this deep dive. Keep refining those streams, keep exploring the mechanics under the hood, and we'll see you next time.